AgentExecutor is good. For a linear task, look something up, do a calculation, return an answer. It's exactly the right tool. We saw that in the last video. But at some point you hit a requirement that doesn't fit in the loop model. Maybe a tool comes back empty and you want to route it to a failover instead of letting the LLM decide what to do next. Maybe you need to write an audit log after every tool call, not at the end during the run. Maybe before a tool executes you need a human to confirm the inputs. None of those are exotic requirements. They come up in real production systems. An AgentExecutor doesn't have a clean answer for any of them, because it's built for one specific shape of problem, a loop that runs to completion. The moment you need the loop to branch, pause, or expose its internals, you have outgrown it. That's the gap LangGraph fills. And the way it fills it is, instead of a loop you don't control, you get a graph you build yourself. Nodes do the work. Edges, including conditional edges with your own routing logic, decide what runs next. And the state that flow between them is the typed dictionary you define, not a private attribution on a class you did not write. Same task as the last two videos, same tools, same answer at the end, but now we will own the control flow completely. Let's dive into LangGraph. LangGraph describes itself as a library for building stateful multi-actor applications with LLMs. Why it is stateful? The graph maintains an explicit typed state of object that every node can read from and write to, not a list of messages buried inside a class that you don't control. Why multi-actor? Multi-agents, or multiple roles for one agent, can run as nodes in the same graph. They share state, they can hand off to each other through edges, and this is the foundation for multi-agent patterns we will cover in video 6, which is the next video. Now, applications, not just the agents. LangGraph is general enough for any workflow where control flow depends on the runtime state. Agents are the most common use cases, but it's not limited to them only. You need to remember 3 concepts when it comes to LangGraph. These are state, nodes, and edges. The 3 primitives. Learn these 3 words and you know LangGraph. Let's talk about each of them. The first one is state. State is a typed dict. It's the shared memory of the entire graph. Every node receives it and returns a partial update. LangGraph merges the update back in. That merge strategy, whether to overwrite a field or append to it, you control with your Python's annotated type hint. Next one is nodes. Nodes are Python functions, and that's it. There is no base class, no interface to implement. You just define a function that takes the state in and returns a state update out. Any Python you can write, you can put it in a node. The third one is edges. Edges connects nodes. There are 2 kinds of edges. Fixed edges that always go from node A to node B. There are conditional edges that call a routing function that inspects the state and returns the name of the next node. The routing function is just a Python function that returns a string. Now let's understand the architecture a bit. In AgentExecutor in LangChain, the control lives inside the framework. That's in a method called iter_next_step. That is inside a class you did not write. It's the class that LangChain framework offers you. When something goes wrong, you have to dig into the LangChain source to understand what the loop decided and why. But in LangGraph, the control flow lives in your routing functions. It's right in the file in your code. It's a Python function you wrote. It returns a string. You can put a print statement in it, a debugger, a database write, or any external API call, anything, and you control everything of it. That's the shift from implicit loop to explicit graph. One more concept before we dive into the code. It's the checkpointing. LangGraph has a built-in persistence layer called checkpointers. When you attach a checkpointer to your graph, LangGraph saves the full state after every node. You can resume a graph from any checkpoint. You can inspect what state looked like at maybe step 3 or step 4. You can replay from step 5 if step 6 failed. We won't implement checkpointing today. That's the full video on its own, but I want you to just know that it exists because it's the foundation for human in the loop and for durable long-running agents. Just keep that in mind. Alright, let's build. On the right, I have opened up the code that we have built in the last video. We are going to build the same agent with the same tools in LangGraph. So let's start with some imports. So basically there are 3 main packages here. LangGraph is to import the graph framework. LangChain Grok is the same Grok integration we built in the last video throughout this series. LangChain core gives us the message types, which are human message, system message, or AI message that LangGraph uses to pass conversation history through the graphs. We have also imported Annotated and operator. These two work together. We use them in the next block to tell LangGraph how to merge messages list when multiple nodes write to it. I'll explain exactly what that means when we start that part. Okay, let's build the next section, which is AgentState. You can see the type of this AgentState is TypedDict. It's a standard Python type, but LangChain uses it as a schema for graphs share memory, the thing that every node reads from and writes back to. In the last video, we used AgentExecutor, which is defined here. AgentExecutor also had a state, which was a step counter, a messages list, or the intermediate results. But where was it? It was inside the AgentExecutor class. You could read it after the run was finished, but you could not read it while it was running. You could not add a field to it, or you could not say, I also want to track which tools have called and how many times, etc. So you could not modify that. With LangGraph, a state is TypedDict, you define. You own it completely, and if you want to add audit log, let's say, or you want to add something else, you can easily add audit logs. Or if you want to add per tool retry counter, or let's say you want to add retry counts as a dict, you want to track whether a human has approved the last action or not, or you want to add a boolean, the schema is yours. You can easily add that to your dict. Now, the messages field has a special annotation, which is list, operator.add. Without this annotation, if two nodes both update messages in the same step, the second write would override the first. You would lose the first message. The annotated tells LangGraph, when merging this field, use messages.add, which means append new messages to the existing list rather than replacing it. That's how the conversation history grows correctly through the graph. The same way we built it manually in our raw agent. But now the framework handles it automatically based on this particular annotation. The other three fields, steps taken, last tool used, and final answer, LangGraph doesn't require these. We added them ourselves. That's the point, because every field in this dictionary is ours, typed, readable at any point during the run. So you can define as many fields as you want. You have that flexibility here. Moving on to the next block, which is tools. This is going to be quick. You can see that in our LangChain we defined three tools in this way. Two tools, web search and calculator. Then we defined memory like this as tool as well. The only difference here is the decorator tool. In last video, we registered tools in a dictionary with a description key. In video 4, which was LangChain, we wrapped them in the tools constructor like this. And here we use tool decorator that reads the doc string of the function and uses it as the tool description automatically. So instead of writing the description separately, it lives with the function body. Less boilerplate, same result. The memory tool still uses pipe delimited single string input, the same way that we use in the LangChain. Okay, let's move to the LLM section. I'm pasting some code here. So in last videos, the LLM produced free form text. It wrote keyword action, then the tool name, and then another keyword action input with a JSON object. We then use regex to pass that text. Sometimes the regex failed. That's why video 4 needed handle parsing errors, which is here. We are instantiating the chat Grok client, and we are using Llama 3 model as our previous videos. Next is a special function, which is bind tools. When you call bind tools, the LLM knows that it's supposed to produce structured output. Instead of writing action and action input in plain text, it produces an AI message object with a tool calls field, a properly typed list of dictionaries with the tool names and its arguments. There are no regex in this case. There is no parser, no handle parsing error function in this case. In LangGraph, the reliability goes up significantly because the model is generating structured data, not hoping you can parse it properly. So this is one of the concrete reliability improvements when you get moving from raw approaches to LangGraph. Let's move to our next section, which is agent node. A node is just a Python function. The full contract is that you pass the state as input, and then the output will be a dictionary with only the fields that you want to update. LangGraph merges your output back into the state. That's it. What this function does, it takes messages out of the state, and then if there is no system message yet, then it prepends 1. This happens only on the first call. Then it calls the LLM, and then it returns a dictionary updating 4 fields depending upon how we defined our agent state. Notice it doesn't decide what happened next. It just does its job, which is calling LLM, updating state, and handing back the result. What happened next is decided by routing function. Nodes do work, routing decides the flow. They are deliberately separate to keep everything clean. Now compare this to the agent executor. Agent executor calls the LLM, but that call is inside a private method called _iter _next_step. You cannot see it without reading LangChain source code. You cannot modify this function without subclassing it. You cannot add a print statement to it without writing a callback handler. Here LLM call is just a function in your own file, in your own code. You can add logging, timing, a database write, an alert, or anything you want in plain Python without touching a framework. Next block is a routing function, which I just mentioned. I'm gonna paste this should_contain function code here. Takes state and it returns a string. That string is the name of the next node to run, or it would be a constant called end to stop the graph. That's the entire API, just a Python function that returns a string. Let's see what's inside. There is a safety valve here. That's the max iteration equivalent from our agent executor. Except here it's a Python if statement. You can see it, you can easily change it. You can make it 5 or for one agent and 20 for another one, so it's easier to set up. You can make it based on elapsed time instead of steps, because you are just writing the Python code. Next is the main decision point. If the LLM produced tool calls, go to tools node and it will return tool string in that case. If not, just stop. That's the entire loop control. Now I want to show you something important. Look at these commented example at the bottom here. Example A, here you want to branch based on what a tool returned. So there is a if statement with one if statement here, which says if the last tool used is equal to web search, you add a fallback search node, add an edge, and you are done. So the routing logic is all yours. With agent executor, you cannot do this. Its path is fixed. As I said, LLM decides action, tool runs, observation, and goes back and repeat. You cannot intercept the result of a tool and change which code or which path runs next. Only the LLM's reasoning can react to a tool result, not your code. Example B is that you want to add an audit log after every tool call. You add audit_log as a list of strings to the agent state. Then you write an audit_node, which is a 3-line function here that appends an entry. You route tools to audit node and audit node back to agent instead of tools straight back to the agent. In executor, you write something like callback handler to achieve this. The next one is human approval before a tool runs. You compile the graph with one parameter, which is this line here. And then the graph pauses before every tool node execution and waits. A human can review the state, modify it, approve it. You call invoke again with the same thread ID and the graph resumes from exactly where it stopped. Agent executor is run to completion only. There is no pause mechanism. This is the architecture because the LangChain architecture doesn't support this flow. All 3 of these examples here is in routing function. You write in plain Python. That's why this block is most important. So you can route your function to anything. Next block is a tool node. I'm going to paste this piece of code here. So tool node is LangGraph's pre-built tool executor. It reads the tool_calls from last AI message, runs each matching function and returns tool message for each result. Those tool message get appended to state messages automatically via the operator.add merge strategy we set up in block 2. So when agent node runs again, the LLM sees the tool results in its message history. This is the direct replacement for the execute_tool function we wrote in the raw agent video, which was video 3. That was like 15 lines of code. This is just 1 line. Moving on to the next section, which is building the graph itself. So I'm pasting this code here. Let's read it like a diagram. So create a graph using state schema. Then LangGraph will validate every node's output against agent state at compile time. Then there are 2 nodes. They are named steps that we already spoken about. Agent is LLM call and tools is the executor. Next is set entry point. Set entry point is when someone calls app.invoke. This starts from here, and then it will go into the conditional edges. After the agent node runs, it calls should continue to decide what's next. The dictionary maps each possible return value to a destination node. If should continue returns the string, which is tools, then go to the tools node. If it returns end, then stop the graph. Next is add edge. After tools run, always go back to the agent. No routing needed. So compile validates the graph, checks for unreachable nodes or any missing edges, and returns a runnable application object. Now let's read this whole thing again, because this is the whole agent flow. So there are two nodes, and there is one conditional edge, and there is one fixed edge here. And the whole loop is agent runs, then tools might run, agent runs again, and until the should continue returns end. This is your entire agent architecture. Let's move on to the last block, which is run and test. So we build graph, and you can see the task is exactly the same as of last video. Then app.invoke runs the graph to completion and returns the full final state or dictionary. Not just the final answer, the entire agent state. Look at what we are printing. We are printing the final result, the steps taken, the last tool used. In AgentExecutor, you get result output for the answer and result intermediate underscore steps for the trace, if you remember to set return intermediate steps to true. If you forget to set that, you won't get that trace. Those keys are fixed by the framework. You get what AgentExecutor decided to give you. In LangGraph, the result keys are the fields you define in your agent state. You can add a field to agent state. It appears in the final result automatically. The output structure is yours. Okay, now look at the streaming bonus at the bottom of this block. Pasting some code, stream gives you the state dict after every node execution in real time, not after the whole graph finishes. It gives you the detail after each individual step. For a 4-step agent, that means 4 state snapshots, every fully typed and each containing every field. You can pipe it to your UI, write it to a database, trigger an alert on a specific tool name, stream it to any WebSocket, all in real time with no extra infrastructure beyond this loop. AgentExecutor has no equivalent. It runs and it returns. LangGraph runs and it narrates how it goes. Let's run our LangGraph agent. Look at the output. There are 4 steps, 1, 2, 3, 4. The step 1 is where LLM plans its first move, which is web search for Tokyo's population, and immediately try to store it using the memory tool. So there are 2 tool calls in step 1. Then the second step is the same pattern. Web search for Japan's population. First it was Tokyo's population, now it's Japan's population. And immediately store it into memory with empty values again. Then step 3, now it retrieves both values it stored in step 1 and step 2 from memory, which is Tokyo pop and Japan pop. Both come back empty because what happened in step 1 and 2 is it has stored the empty values. So this is a reasoning mistake by the model. It's a great example of something you need to watch for batched tool calls. The model here is optimistic. It assumes that it already knows the answer before it confirming it. So that's why the values are empty. But then it calls the calculator tool with both numbers, which is the first Tokyo's population and Japan's population. Now the question is, if these are empty values, where did those 2 numbers come from if the memory was completely empty? The web search results, the LLM still has search results sitting in the message history from step 1 and step 2. It just did not store them correctly. So it's reading the raw numbers directly out of the conversation context and using for the calculation, completely bypassing the memory tool it was supposed to use. The agent worked around its own mistake, which is honestly impressive, but it also means the memory tool was useless in this case in both of these runs. Now step 4 is the final answer, which says the final answer is ready. In here, which is the population of Tokyo represent approximately 11.11% of the total Japan's population, which is correct. So 4 steps, 2 wasted memory stores, 1 calculation that ignored memory entirely, and still the right answer. So look at the final state here. Steps taken 4, last tool is empty, same issue as before. Our agent underscore node, which was defined here, only captures the first tool name when multiple tools are batched together. And on step 4, there was no tool at all. The answer is still correct, but execution was a bit sloppy. Here's why output is actually valuable for this video. In AgentExecutor, you would have gotten a final answer, maybe checked intermediate step if you remember to enable it, and moved on. Here, every step is printed because we put the print statement in agent node ourselves. We watch the model make a reasoning error in real time. We saw it store empty values. We saw it recover by reading from the context instead. That's what explicit state and explicit control flow gives you, not just one correct answer. It gives you the visibility of the whole flow into how the agent got there. And the visibility is what you need when it doesn't get these correctly. We compare the 3 videos we built in this series. Video 3 was 250 lines of pure Python code where we built the raw agent using Python libraries. We built everything ourselves, which including memory, parser, executor, loop. Maximum control was there and there was maximum visibility. Every line was infrastructure that we chose to write. We had great flexibility in that option. Video 4 was 60-70 lines of code with AgentExecutor. The framework absorbed the parser, executor, and the loop. We got a cleaner file but longer debug path and implicit loop and a state we couldn't read in the mid-run. Video 5, which is this one, it's about 90 lines of code with almost none of them are boilerplate. Every line is deliberate architectural decision. The state definition is our schema. The agent node is our LLM call. The routing function is our control flow. The graph wiring is our architectural diagram. The line count is similar to the raw agent for LangGraph video as well. But in video 3, where we built the raw agent, those lines were infrastructure that we were obligated to write. But in this video, we write those lines, but they were the decisions we were choosing to express. That's the real difference between a framework that abstracts away complexity and the one that helps you express it clearly. So when should you use LangGraph instead of AgentExecutor? Use it when your agent needs to branch. If the behavior of step n depends on what step n-1 returned, then you need routing function, and branching, then you use LangGraph. Use it when you need state, that's yours. If you're building anything with observability requirements like audit logs, dashboards, alerting on specific tool calls, you need a typed state dictionary you define. That means LangGraph. Use it when you need to pause, you need human approval, multi-step confirmation, anything that suspends and resumes, that means LangGraph. When runs are long enough that failures matter, LangGraph supports checkpointing, saving the full state after every node so you can resume a failed run from exactly where it stopped. If none of those apply, if your task is clean linear loop and you just need to work it out, AgentExecutor is still the right tool. Don't over-engineer. The goal is always to use simplest thing that works. LangGraph is for when executor isn't enough.